In order to find out the VThevenians across the terminals xy, apply the KCL at node A, that is VThevenians 10 minus VThevenians divided by 20 equals to I1. Here indicated with 2. VThevenians minus V2 equals to minus 1 volt, V2 equals to 10 I1. So VThevenians equals to minus 1 plus 10 I1. So I1 equals to VThevenians plus 1 by 10. So from this equation, if we substitute this equation into this, that is 10 minus VThevenians divided by 20 equals to VThevenians plus 1 divided by 10, that is 2. 10 minus VThevenians equals to 2 VThevenians plus 2, that is 3 VThevenians equals to 8, that is VThevenians equals to 8 by 3 volts, which is option C is correct. Consider the solar cell characteristics given in the figure, which are calculated at temperature equals to 300 degrees Kelvin and the reverse saturation current equals to 1 nanoamp. Calculate the open circuit voltage. Here open circuit voltage for a solar cell is given as Vt, which is the thermal voltage, into load current divided by the reverse saturation current plus 1. We know from the characteristic IL equals to 100 milliamp, that is this one is the IL. IS is 1 nanoamp. If we substitute this one, we will get open circuit voltage as 0.48 volts. Question is, consider the solar cell characteristics given in the figure. Calculate the output power at a voltage of 0.35 volts. For a solar cell, the power output is given as I into V, whereas I equals to IL minus IS e power V by Vt minus 1 V. Here IL is Here IL is 100 milliamps, that is 0.1 into 0.35 minus and 10 power minus 9 into 0.35 e power 0.35. The thermal voltage at a temperature of 300 Kelvin is 0.026 minus 1. If we evaluate this equation, we will get answer as 34.77 milliwatt, which is option A is correct. Question is, an AM modulator has output given by the S of t. We have to find out the modulation index. If we compare the given AM equation with the standard AM equation, that is S of t equals to AC cos omega ct plus mu AC by 2 cos of omega c plus omega into t plus mu AC by 2 cos of omega c minus omega m of t. This is the carrier, whereas this is USB, that is upper sideband. This is lower sideband LSB. Here AC is given as 20 volts. Here mu AC by 2 is given as 6. That is mu is the modulation index, 12 by AC, that is 12 by 20. 4 3 ja, 4 5 ja, that is 0.6. the modulation index is 0.6, which is option C is correct. An AM modulator has given AM equation as output indicated by the S of t. The modulation index is equals to 0.6. Determine the efficiency. Here efficiency of an AM modulator is defined as useful power divided by the total power. We know for an AM PT, that is the total power, equals to carrier power 1 plus this. Mu is the modulation index. So eta equals to PC mu square by 2 is the useful power, that is sideband power, total sideband power, and divided by total power, that is mu square by 2 divided by 1 plus mu square by 2, that is mu square by 2 plus mu square. Here mu equals to 0.6. Efficiency is 0.36 divided by 2.36 equals to 15. Answer eta equals to 15.3%. Question is, consider the system shown in the figure is. Here x of t is the frequency domain sequence, and thus h of f performs the filtering action on x of k, and this block corresponding to a low pass filter whose time constant equals to 1. Here x of k we can write as follows. X of k equals to 4 delta of n delta of k plus 3 delta of k minus 1 plus 3 delta of k plus 1. If we apply the time domain equation, that is x of t, then we will get 4 plus 6 cos 2 pi t, which is a continuous equation. Even though x of k is discrete domain signal, x of t is the continuous time signal. If we apply this x of t to the h of s, which performs the filtering action on the x of t, see, the frequencies present in the x of t are the DC signal as well as the frequency is 1 Hz. Here for this term frequency is 0 Hz. For this term the frequency is 1 Hz. Hence g of t equals to 8 plus 6 cos 2 pi t. Hence option A is correct. Question is, consider the system shown in the figure. Find the DC component signal y of t is. Means we have to find out the DC component present in the signal y of t. Here g of t is given as 8 plus 6 cos of 2 pi t. We are applying the g of t to the low pass filter whose time constant equals to 1 second, that is RC equals to 1 second. The transfer function of the low pass filter is 1 by s 1 plus 1 by s, that is 1 by s plus 1, that is equals to h of s. H of omega equals to 1 by 1 plus j1 j omega. Here the g of t equals to 8 plus 6 cos of 2 pi t. Here omega equals to 0 as well as 2 pi. These are the frequency components present in the g of t. Here h of 0 equals to 1, h of 2 pi, that is omega equals to 2 pi f, f is 1 Hz, so 1 by 1 plus j2 pi. So y of t is equals to 8 h of 0 plus 1 by under root 1 plus 4 pi square 6 cos of 2 pi t. Here the DC component present in the y of t is 8, which is option D is correct.